All right. Hi, everyone. My name is James Beattie. I'm a second year PhD student at the Research School of Astronomy and Astrophysics at the ANU in Australia. And today I'm going to be talking to you about understanding the nature of magnetic field fluctuations driven by large-scale supersonic turbulence. I'm not going to give you much background here. We all know that the universe is turbulent. We know that it's magnetized. When these things come together, they create magnetic field fluctuations. And these are some of the things that I want to describe today. So this is part of a number of projects with a couple of collaborators and supervisors: Christoph Federer, Seto Raphael, Skalatis, Mark Krumholtz, Philip Mox, Roland Crocker, Nico Creel, and Matthew Sampson. So really this talk is kind of based on three different studies. So the first one published by me last year, magnetic field fluctuations in anisotropic supersonic turbulence. This recent one by Raphael, why take the square root, and assessment of intercell magnetic field strength estimation methods. I'll talk more about this at the end of the talk. And a paper in prep right now, led by me, the exact scaling relations and correlation scales for compressible MHD turbulence. Okay, so before I get really stuck into some of the results, I just want to describe the simulation so we can get this out of the way. So I have a whole bunch of boxes as we like to create when we're studying turbulence. So compressible, ideal, MHD, isothermal as well. These large eddy simulations, I have approximately 60 of them. So I'll be talking about around 60 different simulations today in the results, and all with finitely correlated turbulent forcing. So we have our forcing fields only on very large scales. So I'm injecting energy at around the K=2 mode. And I inject with a natural mixture of compressive and solenoidal modes. So not just solenoidal modes. When I say natural mixture, I mean about equal energy in compressive and solenoidal. But a triply periodic domain here, discretized between 144 cubed and 2,500 cubed, probing turbulent Mach numbers between 0.5 and Mach 20, and mean field alphane Mach numbers between 0.01 and 1,000. So the magnetic fields here are composed of kind of the regular coherent mean field component and the turbulent field component, which I'm using delta B in this talk for notation wise. So all this done is with a highly modified version of Flash, and you can check out these studies down here if you want to have a look into some of the modifications that we make. And I'm just giving you an idea of some of the flow field morphologies here. So here you see ray tracing of the density field, lots of shocks moving up and down the magnetic fields, lots of vortical structures set by magnetic field wander. And really this magnetic field wander, you can see it very obviously when you look at the magnetic field morphology in the subalphanic regime, all these very straight fields that are moved around vectored by the velocities around and around on roughly the turbulent outer scale. The supraalphanic regime, you have more of an isotropic mixture of the magnetic fields and the velocities through the fluid. All the simulations that I'll be talking about, all the statistics rather, all the results, every single point in my plots are developed from statistically averaging over 5 turnover times. So any kind of Mach numbers, any kinds of density variance, any kinds of magnetic field fluctuations, I've averaged these over 5 turnover times to make sure that we're not picking up any of these fluctuations here, and we're really getting good statistics. So I run all these for 10 correlation times with the turbulent forcing field, and then I average them when they become statistically stationary. And we're looking at just the last 5 turnover times in all of our statistics. So let's get stuck into some of the results here. So the mean field changes the nature of MHD turbulence. This is probably not appreciated as much as it should be. And I think a very nice way of illustrating this is by computing 3 different alphane Mach numbers here. So this is the alphane Mach number of the mean field, this is the alphane Mach number of the total field, and this is the alphane Mach number of the turbulent field here, averaged across all the cells in the simulations. And here I'm plotting the total in red. So this is the total alphane Mach number, and the turbulent alphane Mach number in blue as a function of mean field alphane Mach number. So there's kind of 3 different domains here. So here the first domain is where the total alphane Mach number is equal to the mean field alphane Mach number. Okay. So this means in terms of energy, the mean field is dominating the energy for these subalphanic flows. This is all mean field. The whole total alphane Mach number is dominated by the mean field. The fluctuating field alphane Mach number is way up here, is very supraalphanic. So this is like alphane Mach numbers of 400 or 50. So And it follows a power law. So the fluctuations are getting more energy as we weaken the mean field, and then they converge around Mach alpha 2. So Mach alpha 2 is this transition alpha and Mach number. Why is it a transition alpha and Mach number? Well, if you look at the delta B over B naught plot here, so this is these are just the magnitudes of each one of these quantities. You can see at Mach alpha 2, something interesting happens. The turbulent energy and the mean field energy become in equipartition with each other. And you see this is where the dynamics kind of changes. So we go down this power law, and then we actually leave the mean field 1-to-1 line. So the mean field alpha and Mach number 1-to-1 line, and we're a little bit weaker. We're sorry, a little bit stronger, and we're a little bit stronger because the fluctuations have a little bit more energy than they would if we were just perfectly following this line up here. So this is where the Mach alpha total is approximately equal to the turbulent Mach number in this regime up here. So the turbulent field is dominating the energy budget in this regime, and the mean field is dominating the energy budget in this regime down here. So my conclusion is that only isothermal subalfanic mean field turbulence exists. You cannot get this fluctuating field into the subalfanic regime. You need a mean field to do this. If you keep going to higher and higher alpha and Mach numbers, all you're going to do is run into essentially the saturated turbulence that you see when you're doing dynamo experiments. So you cannot get a subalfanic fluctuating field in isothermal turbulence, is my conjecture. Okay, so B0 also changes the local turbulent energetics. So here I'm just computing the total turbulent energies locally in a cell. You can see it's going to have this kind of, the velocity term, and also the magnetic energy term. And when you don't have a mean field in there, so you don't have the B0 squared term in there because it's not the turbulent component, all you're left with is a cross field coupling and also the turbulent energy. Okay, you can kind of think that when this turbulence is in a stationary saturated state, that these two things are going to equal each other roughly with some kind of saturation constant. Okay, and then you can ask yourself which one of these terms actually matters the most for different regimes. And essentially for the subalfanic regime, so for Mach alpha and less than 1, you're going to get a balance between the kinetic energies and this cross term here. And this leads to, if you're saying that all the turbulent energies are kind of moving to this cross term, this leads into this equation for the delta B dot B naught over delta B squared relation. So this is kind of a balance between which one of those terms matters the most, the delta B dot B naught or the delta B squared term is equal to 2 over the Mach alpha naught squared. And you can see from our data here that this actually looks really good. So this is not a fit. This is just me plotting this model. So this is if the turbulent energy is being balanced by this delta B dot B naught term. When Mach alpha is much larger, you can kind of argue that this delta B squared term is actually the most important one here. And this leads you to this 1/2 Mach alpha naught over negative 2/3 relation. And you can see in the blue here, this seems to fit the data really well as well. So it's interesting. Locally in the cells, it seems like this delta B dot B naught squared term, or delta B dot B naught term, sorry, is very important for the energetics in the subalfanic regime. So why is this important at all for us who want to measure magnetic fields in the universe and understand magnetic fields from observations? Well, it changes the nature of these dust polarization methods. The DCF method kind of assumes that all the dispersion angles coming from dust polarization are from incompressible shear alphane waves, and that leads to this relation right here. The dispersion angle is proportional to 1 over b. But when we think that this term is the important one in the local energetics, then we get this down here, this new scaling, sigma theta. Oh, sorry, the dispersion is 1 over the square root of b, and you can see it kind of fits the data much better. So this is the yellow line here. This is following this relation down here, this new relation from Raphael in 2020, and this is the DCF method. Essentially, it goes like Mach alpha here and not Mach alpha squared. So definitely read this paper down here. Why take the square root if you want more details on this. But just to give you a very, very brief overview, the relative error between the DCF method and this new method developed by Raphael is quite astonishing, really. So you can see this is the most subalfanic simulations here. Here's the relative error in the DCF. Here's the relative error in this new method. And you can see you get gigantic deviations here for the subalfanic simulations, up to 2,000 to 3,000%. And for Raphael's method, so that's what's plotted on this x-axis, you only get between -40 and 40. So it's really kind of bounded on around 40%, whereas the DCF methods are really inaccurate for subalfanic flows. So the conclusions here, the DCF leads to significant relative errors that grow with shrinking Mach alpha naught, but the ST methods stay within plus or minus 40% relative error, regardless of Mach alpha naught and Mach. So I'll just leave this here, and please read more on this kind of stuff. We have this exciting paper in the works, and please go ahead and ask me these questions in the Slack. Thanks very much.